Now I want to talk about horizontal hydraulic fracture propagation and stress shadows. There are various two-dimensional analytical models that have been used historically. Now we use, three-dimensional computerized numerical, frac simulators. But one issue that's been around ever since, modern hydraulic fracturing was being extensively used, which was basically for the last 50 years, is a question related to what makes a hydraulic fracture stop. Now, in this PKN model, as it's called, we're assuming, the assumption is that there's one-dimensional lateral flow, there's a frac barrier that limits the height of the fracture, and so you simulate the fluid flowing down the fracture in a horizontal direction. But one question that's plagued modeling of hydraulic fracturing for many years has been, why do hydraulic fractures stop? This diagram I've show that if there's fluid pressure acting within the hydraulic fracture, it takes a trivial amount of pressure, something between 20 and 50 and 25 psi. If you're 25 to 50 psi above the least principal stress and that fluid pressure is acting uniformly in the fracture, that fracture is going to want to propagate. So the fractures would just propagate forever. Well, physically that's not very reasonable or intuitive. And so whether they're the two-dimensional models such as the one shown here or they're more complicated three-dimensional models, the assumption is that the fracture toughness, basically the strength of the material that has to be overcome for propagation of this hydraulic fracture, is somehow increasing with size, making it harder for the hydraulic fracture to propagate, and therefore the propagation comes to an end. I've been troubled by this quite a bit, but in fact, it may be reasonable if one looks at the propagation of volcanic dikes. The mapping on the left is showing that when you get out ahead of a dike, you see a zone in which there are multiple parallel fractures with no magma in them. They're just fractures out ahead of the area filled with the solidified magmatic material. That bifurcation process of those parallel fractures might be what we're seeing in the HFTS and the Eagleford data sets. Regardless, Chris Schultz in the diagram on the right looked at systems like the one on the left and actually looked at what could be considered an effective fracture toughness as a function of length and came up with this scaling that's shown, so that as a fracture, in our case, went from to something like 100 or 200 meters about here, the fracture toughness would be about an order of magnitude higher than it is when the fracture is about roughly a meter in size. So when it's a couple hundred meters, the fracture toughness is about 10 times as high. This is kind of a variable that can be adjusted in various frac models, but there may be things, in the fracturing process that we don't fully understand, but then are resultantly giving the hydraulic fracture a scale-dependent strength, which ultimately limits hydraulic fracture growth. And it's quite possible that this is what we're seeing in these data sets. It's pretty clear when you look at this scale, when you have multiple fractures, within a foot or two, or here they're a few inches apart, that these are not opening, there's no fluid in them. The reason for that is what's called the stress shadow, and that's what I want to talk about now. This is a map view of a simulation that's done with a commercial software package, a hydrofrac and reservoir simulator known as ResFrac. And in the leftmost, well, let's start on the right. On the right, there's one perforation. It is one perforation cluster, and it's 0.64 inch diameter perforations in this cluster. And what you see is the hydraulic fracture propagates out about 750 feet and has a width of roughly half an inch over that length of fracture, and all pretty straightforward. The fracture might propagate out ahead, but the prop section of the fracture is on the order. The half length is about 750 feet, and the width of the fracture is about half an inch. Now, if we look at a perforation cluster on the left, and those perforations then have 0.32 inch perforations, half of what it was in the initial case, and you pump into those 4 perforation clusters at the same time, what you find is that the growth of the innermost fractures are impeded. And they're impeded by what's called the stress shadow, and that's because this fracture is opening, this fracture is opening, and the opening of this fracture is increasing the stress in the area between the fractures. Okay, so every time a fracture opens, it increases the stress a little bit. So the opening of the outside clusters, of course, there's nothing here and there's nothing there. So these fractures are only affected by the innermost fractures, but the innermost fractures are affected by each other and the outermost fractures. So these fractures tend to be stunted with respect to the outermost fractures, okay? And we're greatly exaggerating the width, and so it looks a little complicated. But this is a very easy to understand illustration of stress shadows. The 4 fractures are propagating, the outer ones are propagating the furthest, but the inner ones are quite stunted because it requires more pressure to propagate those fractures due to the opening of the outermost fractures. Okay? Now, perforation diameter comes into this because if you open up, you repeat the experiment in panel A, and you simply change the diameter of the perforation clusters, what happens is you only get 2 hydraulic fractures instead of 4. And that's because of this diameter to the 4th term. The friction is so low here that the pressure in the wellbore, it's so easy for all of the fluid to go out these 2 fractures that the pressure never really gets high enough to overcome the stress shadow. And so the perforation efficiency here, as it's referred to, is only about 50%, right? Only half of the perforations are taking fluid, and that's because of the very large perforation diameter. And so as we try to optimize and look at different parameters that might be used, perforation efficiency is important, obviously. You're making the perforations because you want a hydraulic fracture to propagate from each of them, but in fact, if the clusters are too large in diameter, that's not going to happen. Here's some numerical experiments that were done at the University of Texas by John Olson and a student. What he's looking at is 3 simultaneous hydraulic fractures that are propagating. Again, the innermost fractures are not propagating as far as the outermost because of the stress shadow effect. And now what he's looking at is how that stress shadow affects the propagation path. And he's looking at that as a function of the difference between, SH min, which is acting in this direction, and SH max, that's operating in this direction. Now, if that difference is very small, 100 psi, what you can see is that these fractures, which at the wellbore are 50 feet apart, by the time you go out 600 feet, they're now about 100 feet apart. 50 feet and 600 feet, those are still fairly planar fractures, but the proximity of the clusters is in fact resulting in a deviation in the trajectory when the stress difference is as low as 100 psi. So we talked a little bit about how to get SH max and SH min, and we talked about this A phi value, which would indicate, when there was anisotropy between the two horizontal stresses. And in fact, 100 psi almost never happens unless you are in extremely high overpressure, okay, which is rarely the case. So we're going to talk about that soon. Numbers like 500 psi are much more reasonable or even larger, and what you can see is there's almost no deviation whatsoever. I mean, this goes from 50 feet to 60 feet in 600, 10 feet in 600 feet. So it's essentially an absolutely planar hydraulic fracture. So the stress shadow is a real effect. It can be important, but it's also the degree to which it's important has to do with the spacing between the clusters, how you pump the hydraulic fractures, the diameter of the perforations, as we showed before. And now we're seeing an effect of the variation in the difference between the two horizontal stresses at depth. This figure is from work that Norm Warpinski and his colleagues did. And on the left, you're showing the stress shadow. This is the change. The red is the important one, the change in SH min as a function of distance from the hydraulic fracture. Now, what was assumed here is that you have a huge fracture. It's elliptical in shape, 400 feet long, 100 feet high, and there's uniform pressure that's 1,000 psi higher than SH min. Well, I've already talked about this. 100 psi is more reasonable than 1,000, but these are linear results, and what's called 1,000 could, right at the wellbore, could be thought of as 100. So let's think of it in terms of 100, and what it's saying is the stress shadow, the stress perpendicular to a hydraulic fracture right next to the fracture, is about 100 psi, but it drops over 50 feet to about 60 psi, over 100 feet to about 30 psi. If we just divide all this by 10, make that 100, make that 40, 60, 80, and so on. So the stress shadow is real. The stress shadow is going to be a function of distance from the fracture. And in these numerical experiments, what Agarwal, Warpinski, and others were showing was, again, here are hydraulic fractures propagating simultaneously. The outer fractures go the furthest. The inner fractures are sort of reduced in length by the propagation of the outer fractures. Now, this is kind of what we've been talking about in a more detailed type of numerical calculation. One thing that's really interesting about this calculation is that the background color represents the tendency for shear slip. And in other words, if we have pre-existing fractures, what does the opening of the hydraulic fracture, as shown on the left, in other words, there's no leak off, all the pressure stays in the hydraulic fracture. If there's no leak off, there's very little tendency to induce slip, except near the tips of the fractures. In other words, the only place we would ever expect to see microseismic events is near the fractured tip. You're not getting any leak off, any stimulation of slip on pre-existing planes. On the right, they're showing if you allow leak off, every place that's red, you would tend to get shear slip. So you're, in fact, inducing shear slip, well, I'm writing with a red pen on a red background, but you get the idea. You're inducing shear slip in this cloud surrounding the hydraulic fractures. So this is a very nice numerical illustration of this principle I've been talking about, that with slick water, you get the hydraulic fracture plus this zone of shear stimulation surrounding it, and with a viscous gel, you would tend not to. And in fact, early work, this is from Craig Sippola and others, were showing that when you do a water frac and you consider how the position of the microseismic events are evolving as a function of time, with a water as a frac fluid, as a result of the leak off, the events are going further and faster, and you continue to get events over a long period of time. ResFrac, in fact, is simulating that in this case. This is an animation which appears not to be working, but anyway, you can look at the interaction between these different fractures in space and time, and its result of the stress shadow effect on this interaction as multiple hydraulic fractures are propagating. And in fact, here we go, there it is, are propagating and interacting with each other. Pressure is shown in the upper right, the conductivity of the fracture, and which results from the distribution of proppant, and the distribution of proppant itself in terms of mass per area is shown in the lower left. And so, as we think about these pads in a realistic case, these wells were designed to replicate HFTS. The interactions between the fractures are really quite important based on the well spacing and the other kinds of parameters we've talked about. And in fact, we saw some other things that were happening in this data set that were really quite interesting, and that is, as we went from the toe to the heel, we saw the apparent least principal stress increase. In other words, the least principal stress is a function of the Earth, but the measurement of the least principal stress is indicating that the values were going up as the stage numbers were going up. For well C, the well in the middle that was hydraulically fractured in a conventional way, what we see is that the first stage showed a stress of about 3,800 psi. That climbed by 900 psi, backed by stage 9, and then as we approached the heel, they dropped a little bit. And so this was really quite surprising. We've looked for it in other data sets and have not seen this, so it's something kind of interesting that's happening in the Barnett Shale. When we put all the data together, what we see is that the simul-frac, remember this is fast, this is slow, and this is very slow. When it's very slow, this buildup is very small. When it's very fast, the buildup is very fast. And so something's going on here that is rate dependent, okay? And when you start putting a lot of fracs in very quickly, what you can see in wells A and B, that there's a big difference. When we start, they're all about the same, as they should be, okay? But there's a rate dependence that's affecting the treating pressures and the apparent earth stress, or the earth stress as affected by the fracking process. What I believe is going on is that in addition to the opening of the fracture, which is causing this stress shadow, there's a poroelastic change. In other words, the pore pressure is changing around the hydraulic fracture, and that change in pore pressure is changing the stress as well. And this is some modeling that was done with the GeoSim simulator developed by Tony Satari that actually shows an area of enhanced stress, which was caused by that leak off of pressure and the coupled poroelastic stress change. Okay, so the mechanical effect of opening causes a stress shadow, but there's also a stress shadow caused by the poroelastic effect. And of course, because the poroelastic effect depends on the diffusion of pressure, the poroelastic stress change is going to be very rate dependent. Okay, and the faster you go, the pressure increases quickly and doesn't bleed off between the individual stages, because the stages are occurring, right after each other, and so we see a big poroelastic change in that case. Whereas if we were doing it very slowly, the fluid pressure change would be dissipated, the poroelastic stress would be dissipated, and therefore the effect of successive stages would be relatively minor, all of which is consistent with what we saw. We go fast, we get a big effect. We go slow, we get a very small effect. This too can be simulated in ResFrac. In this simple example, the upper example is showing that when stages are separated by 12 hours, you wind up getting 3 fractures propagating in the second stage. But when they're close together and the stages are only 2 hours apart, we lose the hydraulic fracture coming from one of the perforation clusters due to that poroelastic stress change.